Hello everyone, welcome to Watch Complications. I'm Brian. This video is making custom dials part 2, 3D printing dials. So I'm going to take you through my process of creating a dial blank using 3D printing. But first, a couple of things. Number one, make sure to subscribe to the channel if you haven't. Follow me on Instagram at watch_complications and check out my blog, watchcomplications.com. Second, I'm about to release a new watch series called Tea Party. This will be on my blog and Etsy store, the information about the new series. So the first model is named Earl Grey. There will be plenty of pictures and such. Very soon there will be a video that shows me building the second currently unnamed model in that series. But it'll be a nice, again, video, sort of a counterpart to this one that shows me building a watch in its entirety and putting that all together. And the third thing is, what am I wearing today? It's my Alpha DMC Silver. There's a full review on YouTube and on my blog, so that was a couple months ago, but check that out if you haven't. It's actually one of my favorite quartz watches, one of the few that I like that actually has a cushion case on it. So the Alpha DMC Silver by the DeLorean Motor Company. A nice and nostalgic watch, particularly for someone like me that's a Back to the Future fan. All right, now let's talk making dials. And as with all things watches, it starts with the movement.
Alright, so first I want to show you my process of designing the dial blank, and then I'll show you me printing a dial blank, and then in a future video in this series I'll show you how I go about then printing the actual indicators and logo and things like that on the dial. So what you see in front of you is a specification document for a Solida movement. Right now I'm working on a project for a customer that has a GMT movement, specifically the ETA 2893. What's nice is Solida publishes the specification documents for all of their movements, which are equivalents of the ETAs. And so if you want to know all the parts, the layout, the design, how to put them together, Solida publishes the spec docs for these things. So this is the spec doc for the Solida SW330. Which is equivalent to the ETA 2893, which is the actual movement that's going into this GMT watch for a customer. So I need to create a dial for it. And one option for that is 3D printing. Now these are extremely detailed specification documents, which has everything you could imagine about it, you know, heights and power reserve and components. There's parts list. So you can see here, I'm kind of just quickly skimming through parts list. And here's all the actual parts, sort of visuals of each of them, so you know what they each look like, that are numbered to coordinate with the list. And then you get down into the instructions on how to put the movement together, what oil to put in what spots, so on and so forth. So there's extremely great documentation, which is really a tutorial if you want to take a movement apart and put it back together. This is the number one resource I would look at when taking one of these movements apart or putting one together. But one of the things in this specification document are all the measurements of the movement overall and its different components. You can see here there's the movement from the side, which shows you, for example, how big the stem is, where it goes in relation to other things, different heights, thicknesses of different components of the watch. And one of the sections in here are the indications for the dial. As you can see, there are 3 different languages here. English is the third in all parts. So you can see indications for the dial's third here. Then down here, you see that dial fixed by keys. Again, English is the third one down, which is a language I speak. And here's a side view of the dial indications. And you can see here, everything is in millimeters, by the way. So just keep that in mind. Particularly for those of us in the US, everything is in millimeters, which is nice. So you can see here that the height is 0.4 millimeters, which is a pretty standard thickness for a lot of dials for these, Swiss and ETA, Solida movements. What this also tells me is, the thickness should be about 0.4. Also tells me how long to make the dial feet and their width. So width and height of the dial feet is indicated there. Grab those measurements and draft those. Here's a side view, which shows me, again, there's going to be, notice there's this shaded area. The shaded part is the dial. So that's the actual design. Here's the date window. This particular movement has a date wheel. You can see there's white space under here, so there's a recess in the dial. So the overall thickness would be 0.4. There's this recess that is 0.14 millimeters, and that gives this center thickness 0.26 millimeter. So those are things you have to take into account. A lot of dials are just solid. This one has a little bit of a recess to accommodate some of the movement components there and toward the center. And then if you go down just a little bit more, you can see, well, how large do I need to make the center hole? In this case, 2.3 millimeters about. A lot of the dials are about 2. I've been measuring different dials for this movement. A lot of them are around 2. Notice the date window, the height you want to cut. We're going with the center here because we're not doing a bevel edge, is 2 by 2.7 millimeter. The dial feet locations relative to the overall size of the movement would go in these locations. So taking all of this information from the specification document, I can go into AutoCAD and draft a design. And that's what I'm going to do now. All right, so if you're going to create your own watch dials, whether that's creating a design that you could then send to a manufacturer and create like brass dial blanks for a particular movement, or if you're going to do what I'm doing, which is design it and then export it to an STL file for 3D printing, you've got to get familiar with AutoCAD or some sort of a drafting software so you can create and design these things and have all the specifications exactly what they need to be so it can be printed or created in sort of the manufacturing step. This is, of course, just the design. All right, so what you see here is the beginnings of the dial blank. I've gotten it started so I can just show you the more interesting parts. Right now, this is really 2D. It's just a flat surface, and all that's 3D at the moment are the dial feet, which you can see here and here. So I've already placed those in the drawing. So one very important thing to be aware of if you were going to do this. If I was going to create this dial in AutoCAD so that it could then go to a manufacturer to produce an actual metal blank, I would draw it exactly to the specifications that are in the document. However, I'm 3D printing, and 3D printing is by no means perfect yet. So my 3D printer, which is a Lulzbot Mini 2, has a micro extruder that can print in layers that are 0.05 millimeters thick. So think about that. If I'm printing something that's 0.4 millimeters and it can print in layers that are 0.05, then that means I have essentially 8 layers of material. Now, what I've learned about my printer specifically is that if this is supposed to be 0.4 millimeters thick, I actually need to spec this under, like 0.3, 0.35. It will print a little bit over 0.4 at about 0.45, 0.48. And then if I want to get it back down to the appropriate size, I can sand it down. So what if I was to print at like 0.3? Well, it actually might not come out that great as a print. It might be too thin and flimsy. It's got some gaps in it, etc., etc. I much rather print a little bit on the higher end, a little bit thicker, so I have a robust piece of material, and then I can sand it back if necessary. So that's just something you have to, trial and error, play around with, given your printer, and just something to be aware of. All right, so let's finish making this dial blank. So what I'm going to do is, this is just sort of a starting point. I'm going to copy this to another spot so then I'm using that as a starting point. What I'll do is I'll just create a bunch of these and then try different thicknesses and print those different thicknesses and see which specification works best, and then I can work the blank down as necessary depending on the case and the movement, so on and so forth. All right, so I've got a copy of it now. I want to make this dial, I want to do this one to spec just to show you. So I want this to be 0.4 millimeters thick. So I'm going to turn this from 2D into 3D. So it's going to be 0.4. So you can see now I have a dial that has a thickness to it. Now everything was flat, 2D, and I've got these dial feet, but they were attached, you might think of, to the bottom of that flat surface. So now that I've moved the thickness of the dial down, I need to move the dial feet down so that they are against the bottom edge of the dial. So I'm actually going to move the dial feet down, and I'm going with the center of the dial as my point of reference, and I'm just going polar. And AutoCAD has these nice features where it'll sort of auto-click if I want to go a certain direction, like wanting to go up, wanting to go down on the Z-axis, as you can see, negative Z, positive Z. So I want to move these down, and I'll move them down 0.4. You can see in here I had a radius, sorry, a circle. That was the top of one of those things, so I'm going to delete that. All right, so now the bottom of the dial and the dial feet are in the correct spots. I also need to move this down. This was all one flat surface to start with. I need to move this down to where that recess will begin. The cutout needs to be 0.14, so this thickness is going to be 0.26. So I'm going to do a move of this inner circle that's 16 millimeters, and I'm going to move it down 0.26 millimeters. Again, I've changed the units in AutoCAD to millimeters from instead of inches. So I'm using the metric system instead of the US system for measurements. So everything I type in is in millimeters. So I've moved that down. Now I need to add thickness to this so that it can cut through the rest of the dial. So what I'm going to do is, it's called press pull, which is what I use to create the thickness anyway. So I'm going to drag this down. It doesn't matter where I put it. Now I can subtract from the dial this component. And you can see there's a thickness there that's not as thick as this. So this would, what's on top of this dial is 0.26, and then the recess with what was left would be 0.14. So basically I just subtracted that large central cylinder from the overall dial, and it cuts it back. So we can look at this in a different way. So I can flip to conceptual. You can see it's still solid on the front. If I'm to flip to this and look underneath, here's my dial there. You can see there's a recess underneath. And there's the dial feet sticking down. And there's different ways you can look at this depending on what you prefer. Hidden, I'll show you just what a couple of what these look like. Realistic kind of shows it where you can see the recess in there, dial feet on the bottom. And I'll show you what this looks like once it's fully built. Let me get this back to where I was. All right, now what I need to do is cut the holes for the center and the date, and then we'll really be done. So what I'm going to do is, again, I want to pull these things down like that, and then I'm going to subtract those things from the dial, and you can see it sort of bores the holes in there. Let me go back and show you the conceptual view. See, now I've got a center hole and a date window that recesses underneath. But that's basically it. I've got my dial. And what I can do now is I can export this, and the type of format I want is STL, which is lithography. And I'm just going to call this temp. Save this off. Now I'm going to select the components that I want to export, and these have to be essentially solid meshes. As you can see, select solids or watertight meshes, things that are next to each other so it can form a 3D model out of it. And so I've got all the stuff I want selected. Really, it's just the dial and the dial feet. I'm going to hit return, and that will have exported my dial. So now if I come over here, I'll see temp.stl, and notice in this rendering I have got my dial, which is really cool, by the way. This sort of quick look view. I'm on a Mac, and you can see here I've got my 38 millimeter dial. I've got my center hole, date window, the dial feeder on the back. There's the recess to accommodate the movement. Now this I could send to get manufactured in any kind of metal I would want, but I'm going to use this STL file to bring this model into my 3D printing application, and I will print this dial. Let me show you real quick though, the one that I'm actually going to print. So this one's easier to show creation of the dial. The one I'm actually going to print is for a different project, again, that I'm working on for a customer. And this one has a dual time window, which you can see took a little bit more work to get that cut into it, but this is the one that I'm actually going to print for this example in the next step.
Okay, so now we're ready for taking the STL files and 3D printing them. Here you can see a couple examples of STL files. The thicknesses are different than what we just actually drew in AutoCAD, but here is the dial that we just drew for the GMT project. You can see there's the center hole and the date window. On the back you can see the recess and the dial feet in the appropriate locations. Here is the dial that we're going to actually print, however, in this example. We're going to watch it in high speed, so you don't have to watch the whole 30 minutes that it takes to actually print this. You can see there's the window cut out for the dual time, date window, center hole, which is a little bit smaller for this movement than the other one. This is solid the whole way through. There's no recess, but the dial feet are in the same location. And this is actually 35.6 millimeters in diameter, but this is the one we're going to actually print. So what we'll do then is launch my 3D printing software, which is Cura, the Lulzbot edition, because my 3D printer is a Lulzbot Mini 2, which I'll show in just a second once we actually watch it print, again in high speed. I take my STL file that I want to print and I load the model into the window here. And the first thing I'm going to do is rotate it so that the dial feet are up. See me rotating it. I'm going to lay this flat. I use the default settings usually, except that I have the micro extruder, so I'm taking this up to ultra high detail, which takes a little bit longer, but you can see my layer height is 0.05 millimeter, so super high detailed, and then I'm going to send it to my printer for printing. You can see this takes about 26 minutes to print this particular dial. And that would change based on the different settings. I'm just using a regular old white PLA to print these dial blanks, and off we go. So just for reference, this is my 3D printer. It is a Lulzbot Mini. Now I just want to show you what these 3D prints can look like up close. Now these can come out sort of widely varied depending on, again, what exact printer you have, what type of material you're using. I'm just using a kind of a standard, low cost white PLA material in this printer. You can use all kinds of different things. This is the dial we just watched being printed in high speed mostly. And this one is solid the whole way through. You can see that there's some remnants that need sanded off. What I have to do is take a X-Acto knife and clean up the feet a little bit so that they are the correct size. Kind of normal things you would have in cleaning up a 3D print if you've done any sort of 3D printing of other objects. But you can see this looks pretty good. Now if I need to, I can sand it down and then prime it and get it ready for printing. So that's the one we just watched. And then here's an example of a print from the GMT project I'm working on that just had the date window. You can see the light kind of coming through the center section because it's, again, a little bit thinner because of the recess on the back, and you can kind of see it in here. And this is pretty thin. I mean, this is around 0.4 millimeters thick, so nice and thin. You'll notice that it's quite flexible, which is both a pro and a con a little bit. Very different than a sort of standard all metal dial blank. But prints come out fairly nice sometimes, not always. So what you can do is use these as a nice base moving forward with an overall dial design. Sometimes I just use them for practice. So for example, here's a dial that wasn't gonna work, wasn't gonna get used, so I just tore the dial feet out, and now I use it to punch holes into material like cardboard that I want to use to hold onto dials while I'm sanding or printing them. So it's kind of a template to tell me where to put holes and mark holes for the dial feet. So sometimes I also use these 3D prints just for testing printing. Now this isn't centered or anything, but it will give me an initial look visually at the overall design of a watch without costing me next to anything. So it's a way for me to test printing and to get things like my pad printer centered well and things like that for actually then printing the final dial samples that I have for a project. That's the GMT project, by the way, if you didn't notice. All right, so that's an up-close look at a couple of the samples that I've printed, just to give you an idea of what sorts of things might be possible with 3D printing. All right, so there's some more insight into one of my methods of creating a custom dial. And that's sort of the initial phase of creating a custom dial blank. In the next video in this series, I'll be showing the steps of sanding, priming, and printing on both metal and 3D printed dial blanks. So thanks for watching. Don't forget to subscribe and keep on ticking.